Right, class, we're going to start with testing the second rod right here. This is the aluminum one. You can see right here in the Tensile Tester window, it says it's aluminum. I'm going to go ahead and put it in, and we're going to start the test and see what happens. So you can see it's stretching. You can see the necking right there, and then we have failure at the end. So here's our graph that was presented to us, and let's go ahead and analyze it. All right, students, so here we have assignment 232, Tensile Testing. Today I'll be doing questions 1 through 4 from the aluminum example that we just did. After this, you guys will be doing questions 1 through 4 for the copper example. So you can see question 1 is up here in the top right, and it talks about proportional limit stress. So remember that the proportional limit is pretty much from the beginning right here of your data, and it's pretty much a straight line, almost always is a straight line, and that's what keeps it proportional, the fact that it's straight. When it's curved, it's not proportional. So you can see that our proportional limit goes from the bottom to about right here, okay? So it's asking me to put the graph result right here. Well, I have the graph right here, so I don't really need to do that one. The second question is asking me to locate the proportional limit on the testing graph. Okay, so the proportional limit is where the elastic limit is, and that's going to be right here. Okay, so done with that one. Check mark. Okay, so we're going to now solve for the proportional limit stress. Okay, so we're going to do that using this stress calculation, or sorry, stress equation, which is stress equals force or load over the area of that load, the cross section of the load. Okay, so let's go ahead and get started with that. So in order to do that, I need to know the formula, which it gives it to me. So that's a piece of cake. I'll just copy it. Sorry for the writing. I'm getting used to this writing tablet that I have. So when I start doing this problem, I immediately notice an issue. My issue is that the data given to me in this graph is in metric. As you can see, the load is given to me in kilonewtons, and I need it to be in pounds. So I'm going to need to convert that. So if I look it up on Google, I should see that 1 kilonewton is equal to 224.809 pounds. Okay, so that's the conversion I'm going to use. Later on, when I get to other questions, I'm going to also have to do the same thing for millimeters to inches. Okay, so let's start with force. Okay, so I'm going to start with the force up here on top. So my force, it looks like at the proportional limit is 20 kilonewtons. So in order to do that, that's a piece of cake. I'm going to get out my calculator. Since it's 1 kilonewton for 224 pounds, I'm going to multiply 20 times 224.809. And I'm going to go ahead and hit equals, and that's my answer. So it's going to be 4,496.18 pounds. So that's going to be my top right there, 4,496.18 pounds. All right, awesome. All right, so I got my force there. Now all I need is my area. So if you can look above question 1, it actually tells you what the original diameter of these dog bones are that we broke. And if you look up there, it'll tell you that the original diameter is 0.2 inches, which is good because it gives it to you in metric and inches, so I don't need to convert it. So 0.2 inches. Now, I don't need the diameter because for area, it's a circle. The cross section is a circle. So for area of a circle, you should know that it's pi r squared. So instead of using the diameter, I need the radius. So it's pi. The radius is half of the diameter, so it's 0.2. It's going to be 0.1 inches squared. Okay, so I'm going to get out my calculator again, and I'm going to go ahead and do this one. So 0.1 squared, first of all. Do it the right order, and then that changes to 0.01. It's getting smaller, and then I'm going to multiply that by pi, which is right here. That's what pi is. I'm going to hit equal, and I get 0.0314. Okay, so I'm going to move that down here, 0.0314 inches squared, because it is area. Okay, I set up my problem. Now I just need to work it out, and I can do that with the calculator again. You don't have to do it by hand. You could go ahead and do it with the calculator. 1/8 divided by 0.0314, and here's what I get. All right, so I get a big number here, 143,190. So that's big. Because it's so big, you know that I can round my answer, and because it's such a big number, I can actually round to the nearest thousand, so I don't have to go, put this all in detail. So I'm going to go ahead and round to the nearest thousands for this one. So I should get 143,000. Now, it did talk about this in the slideshow, but just so you are aware, we are left over with pounds over inches squared. But the way we interpret that is as PSI. And PSI stands for pounds per square inch. So per is another way to say divided. So we got pounds up here per square inch, PSI. So anytime you're left with pounds over inches squared, just go ahead and automatically convert it to PSI, because that's pretty much what it is. Okay, so that's question number 1 done. Not too difficult. Once we have our conversions, we should be good. Let's move on to question number 2. All right, so here we are, question 2, which is now talking about the yield point stress. So pretty much you can see that it's the same exact question, but now it's just, instead of talking about the proportional stress point, it's talking about the yield point. So you should have learned in your slideshow that the yield point does not have a very well defined point in most cases. And for the aluminum, it really doesn't have one. So the yield point does come after the elastic limit, but in this case, there is not actually a defined yield point. You can see right here, once again, just like in the last one, we went from the elastic limit almost immediately to deformation. So for this question, it's actually really easy for aluminum, and it might be the same for copper, so pay attention when you analyze that graph as well. Since the yield point is almost immediately after the elastic limit, all my equations are going to be the same. The question to locate the yield point, well, since there's no well-defined yield point, it's going to be right there again. And then to solve for it, well, if it's right next to the elastic limit, then I'm just going to get the same answer I got last time, which, if you remember, was 143,000 PSI. Now, I will tell you this, if you were able to run these experiments on your computer, there was one metal that you could have run, that actually did have a very well-defined yield point that was not the same as the elastic limit. But we can talk about that later if you guys want. Let's move on to question 3. All right, question 3. So for this one, same thing, solving for stress. So you can see right here I brought in my equation and my conversion for kilonewtons to pounds. So pretty much this is talking about the ultimate tensile stress. So this is going to talk about the maximum load. So if you remember from the slideshow, the maximum load is pretty much exactly what it sounds like. It's the maximum amount of force that your material can take. So it's asking us right here to locate the maximum load. I'm going to say it's right here. Okay, there is the maximum load. That's as high as that graph gets, right there. Okay, so now we need to determine what number that is so we can run the equation. So for the last one I had over here, it was 20. This one looks like it's more than 25, but not really more than 27. Because 27.5 would be right in the middle, right here. Let's go ahead and say 26. 26 seems like a good number. So we're going to do 26 kilonewtons as our maximum. Okay, so of course we need to convert that over. Let's go ahead and get started with that. So force, I'm going to get my calculator out again. 26, and I'm going to multiply it by 224.809 to give me pounds. Ooh, that's a big one. Okay, so 5,845.034 pounds. Let's go ahead and write that down. 5,845.034 pounds. Okay. The good thing is the diameter, the area of our dog bone didn't change because they're all the same size. So we can reuse that number. If you remember, it was 0.0314 inches squared. Okay. So, okay, good. Now we just need to get out the calculator again and run this calculation. Oh, I have it up there. So I'm going to go ahead and divide it by 0.0314. And I get 186,000, and I can round down to just 186. So my answer for this one is going to be 186,000 PSI. Remember, pounds per square inch, PSI. Okay? All right, number 3 done. See, this isn't so hard. Let's move on to number 4. All right, question 4. Once again, talking about stress. You can see I brought over my equations, my conversions again. And for this time, it's talking about the breaking or rupture point, or I like to always call it the failure point, where it fails. So it wants us to locate where this failed. That's really easy. Whoops, I need to grab the pen. The failure point is right here. Okay, so that's where it fails. So just like with the last 2, we're going to go ahead and take that number and use it as our force. So let's fold this back. It looks like that's going to give us a 16. I'm going to use 16. It's close enough. All right, so I'm going to use 16 kilonewtons. However, I need to convert it over to pounds. So 16 times 224.809, and I get 3,596.944. Okay, 3,596.944 pounds. Okay, and once again, dog bone's the same exact testing material here, so same diameter, or same area, excuse me, 0.314 inches squared. All right, I'll put that there, and let's go ahead and calculate that by dividing it by 0.0314. And okay, 114,552. I'm going to go ahead and round up on this one. So I'm going to go ahead and say that it's 115,000 PSI. Getting mixed up there. All right, so that wasn't so difficult, guys. As you can see, going over your notes probably will help you with this, because the point is asking you to find. You can find, if you don't remember, which you probably don't because there was a lot of information in the last slide, you can go ahead and look at your notes to go ahead and locate those points. But questions 1 through 4 on the copper one are going to ask you for the exact same points, so you should know exactly where they are. Don't forget to convert your kilonewtons to pounds, because otherwise your answer will be incorrect. Now, one thing that you can use to help you is you can go ahead and save this number right here, because that number is the same for the copper dog bone. It's the same size, so you can reuse that number. You're really just going to use different force numbers. Okay, now let's run the copper one. The copper one's going to be this last one down here. I'm going to go ahead and snap that into place. I'll go ahead and start it, and we can check out the results. And there it is, we have failure. Here's our graph. I'll put up a picture so you can analyze it and run your numbers on it.